The title of this presentation is Quantum Inverse Scattering in Three Dimensions for the 20-vertex model up to Dynkin automorphism. So we'll begin with a summary of previous presentations on the quantum inverse scattering type approaches, and we'll be exhibiting how these types of approaches can be of interest in further detail, how they can be described in three dimensions, and how this relates to certain algebraic structures and properties. So we'll be recapping like how we introduced in some previous presentations that we described the six-vertex model, and even though this is a model that can also be described for or defined for discrete probabilities, it has a lot of interest for integrable probability and looking at combinatorics and geometry. And we can also look at this wide variety of characteristics from the model results from the definition of the R matrix in the Hamiltonian flow. And we also drew upon similarities of computing the action angle variables for the nonlinear Schrodinger and Kamasa-Home PDEs. And we also discussed aspects of a conjecture for integrability of the Hamiltonian flow, which is shown to hold for the inhomogeneous six-vertex model that can be analyzed from a conjecture and a suggestion from Keating, Reshetkin, and Sridhar. And we provided an overview of those types of computations with the action angle variables on the Poisson bracket. So all of these previous bullet points and objects that we defined for the quantum inverse scattering approach, they're related to the fact that we can demonstrate how notions of the quantum inverse scattering approach change with additional assumptions on the R matrix and the L operator. In one case, we don't look at a universal two-dimensional R matrix. We just look at a different type of R matrix, which poses some different types of constraints or different types of conclusions that we can glean and gather from the quantum inverse scattering approach, as well as the fact that the L operator, it can be written in terms of different types of basis functions. In the one hand, like how we didn't really emphasize this in previous presentations in the series, but on the one hand, you can define an L operator more in terms of a Pauli basis. And the Pauli basis, they come in play from quantum mechanics because they're describing certain characteristics and non-intuitive characteristics of particles and also ensembles of particles that have to satisfy the Heisenberg uncertainty principle. But the fact is that there can also exist other types of representations for L operators when you're looking at a tensor product of two spaces and looking at constructing the universal R matrix in that type of setting. And when you look at the tensor product of two spaces, this poses a lot of different types of terms in contributions from different entries in the R matrix that appear from taking tensor products of differential operators. So in the previous presentations, we drew some of the attention to the viewers to the fact that from the three-dimensional L operators, which we can construct from in tandem, with the universal R matrix, there can be, different complex value functions, which are mappings into unital associative algebras. And this completely differs from the fact that the entries which appear in the two-dimensional L operator, in other cases for domain wall boundary conditions at the six-vertex model, and they can be other classes of L operators, they can be expressed in terms of Pauli matrices. So there's completely a difference in the construction of these two entries, which is going to be related to the Cartan matrix, which will be further describing the reference, and then we'll be able to circle back and return to some other types of notions of integrability that we had mentioned in a previous presentation and demonstrate how this different structure L operators, it has some different types of ramifications and different types of conditions that it poses on the conclusions that we can gain from this quantum inverse scattering type approach. And like we have been mentioning, the computing the action angle variables, it has a connection with the nonlinear PDEs through the Kamasa-Home PDE, because we can form a system of Hamiltonians like we had defined in a previous presentation, as shown in this paper by Konstantin and Ivanov. And they're interested in looking at some type of Poisson structure associated with the Kamasa-Home PDE. So this is just a different type of Poisson structure in which they're maybe looking to look at some Poisson brackets and perform computations with these Poisson brackets. But for the inhomogeneous six-vertex model, because we have a different type of R matrix as well as a different type of Hamiltonian formulation, this influences the type of Yang-Baxter equation and the equality from the two partition functions which we're asserting for the two models are equal, as well as from the fact that in comparison to the Hamiltonian system that's defined for the Kamasa-Home PDE, that system consists of defining it with two Hamiltonians, whereas the inhomogeneous six-vertex model, in the presence of those inhomogeneities, it only has one Hamiltonian flow. that the authors from Katie Reshettigan and Shrikar conjectures to be integrable, which can be shown by making use of references for computation with the Poisson bracket of the action angle variables. So, but besides the Kamasa home PD reference, seminal work from the following seminal reference can be adapted for the inhomogeneities in the 6-vertex model. So, like we have been mentioning, as just part of our very brief review before we dive more into the 3-dimensional case, is the fact that the Fadiv and Takatan seminal reference for the Hamiltonian methods and the theory of solitons, it's very much an invitation and is very encouraging to try to look to see where these types of results can be adapted in higher dimensions in the 3-dimensional case. But the thing is that if we look, we have to keep in mind that if we look for different types of L operators and they have this type of structure from the up to Dynkin automorphism from the Dynkin diagram, there can, even though we haven't really defined formally what the automorphism or the Dynkin diagram is, still from a distance we can look at and understand how we can generate some type of more general set of relations from looking at different types of families of L operators, as well as relating it to the Dynkin automorphism, and looking at from this action of the Dynkin automorphism, whether there be any broader set of relations which would hold, and how the types of computations with the Poisson bracket would be carried out, and how we can still make use of some information, albeit limited information, from the 2-dimensional case with the Poisson brackets and the computations with the Poisson bracket that we did in that case. So like we've been saying, the task of interest is that we want to look at further analyzing and breaking down, applying the QIS type approaches from the 2-dimensional case, but applying this for the 3-dimensional case and thinking about different types of connections and impressions we can get. And like we had also mentioned in the second presentation or earlier presentations in the series and how we have been reiterating, is that we have different terms which appear in the entries from the 3-dimensional L operator, which is motivated from the construction from the tensor product of two spaces. And we have tensor product appearing of differential operators, because this D1 guy that's raised to first that we raise to the power D1 from the Q is given by the fact that the D1 is given by the tensor product of a differential operator with an identity, as well as the D2 operator is just given by the identity with the tensor product with the differential operator D. So we're just permuting the order in which the identity operator appears in the tensor product, either in the D1 or the D2 differential operators. So that's exactly exhibiting and clarifying, in light of some additional motivation in the material that we've been reviewing from the previous presentation in the series, how the tensor product space, and as well taking operators or tensor products of identity operators with the differential operator comes into play. And this is obviously all related to the first characteristic of the L operator that we had described, which was the mapping into the unital associative algebra, which is the complex value function Xi. And so like we have been saying, even if we're looking about different cases from the 2 or 3-dimensional case, we'll still need to define and make use of the Poisson bracket. So this is given by the fact that, like we had defined, but just very briefly to reiterate, the Poisson bracket of two arguments f and g is given by I times the integral over minus L to L times the subtracting of these two derivatives. And this was originally introduced, like we have mentioned, from the seminal work of Hadib and Takajan for the nonlinear Schrodinger's equation, because they were looking at the solutions Xi, which is the wave function, which is the solution to the nonlinear Schrodinger's equation that they have mentioned. So they're differentiating each one of these test functions either with respect to the wave function or with respect to the complex conjugate of the wave function. And like besides the tensor product, we can also or besides the Poisson bracket, we can also take the tensor product with the Poisson bracket between these two arguments A and B, which just amounts to asserting a tensor product in between each one of the derivatives in comparison to the first tensor product, which was defined above, which is just multiplying these two mixed derivatives with ordinary multiplication instead of with a tensor product. But this other Poisson tensor product or tensor product of the Poisson bracket still has I per factor in front of the integral taken with respect to the standard Lebesgue measure over the real line. And so the Poisson bracket of the tensor product of two entries emerges in several computations with the Poisson bracket from the entries of the transfer matrix. So this is just to say and reiterate and reemphasize that this type of expressions and these types of computations, we're obviously not going to be able to escape the fact that we'll be needing to further expand on the computations of the nine Poisson brackets that were computed for the first set of relations from the Poisson bracket, the entries of the transfer matrix. And then in 3 dimensions, that's obviously going to hold for greater than 9 terms, which is going to exhibit some type of generalization that we're exhibiting along with this richer algebraic combinatorial and geometric structure from the universal R matrix that makes its way into the 6-vertex model. And from the L operators to the set of 16 relations from the Poisson bracket from the entries of the transfer matrix, it's just to say that, like we had just mentioned, in the 2-dimensional case, we already have 16 relations. So in the 3-dimensional case, as we lift to a higher ambient state space for looking at the 6-vertex model, there's going to be undoubtedly many more components which appear that we'll have to take the Poisson bracket of, which will collectively together describe some characteristics of the Poisson structure from the Poisson bracket of the entries of the transfer matrix. So at least in 2 dimensions and in 3 dimensions, this type of interpretation and types of characteristics of the Poisson structure, it'll still hold. And like we had mentioned in the 2-dimensional case, the approximation of the first Poisson bracket in the set of the 16 relations for the homogeneous 6-vertex model takes the most simplest form, because we have some perfactor, which is a sine of 2a term raised to some positive power, which is squared, as well as multiplying this perfactor for the sine of 2a term for 2 terms of u minus u prime, as well as u prime minus u. So this is just exhibiting the fact that when we're performing certain computations with the Poisson bracket, it would really help us and behoove for us to look for ways to obtain entries of the transfer matrix within the 2 arguments for the Poisson bracket, which are either dependent upon u prime or u, or u or u prime, because by the anti-commutation property of the Poisson bracket, we can just anti-commute these 2 functions to obtain u from u prime or u prime from u, and so on and so forth. So it's just really helpful to try to look at some base case for computing terms of the transfer matrix of the Poisson bracket, and how this simplification is related to the fact that a sine of 2a term appears in both of the arguments for the Poisson bracket, for the first Poisson bracket within the set of the 16 relations from the Poisson bracket from the entries of the transfer matrix. And additional complexities emerge from computations of the Poisson bracket in the 5th term. So in the previous presentation in this series, we described the 2nd and 3rd term, and we related it to the 1st. And then we even went up to the 5th term, and we drew some similarities from the 5th and the 5th, or the 5th Poisson bracket and the 1st Poisson bracket. But there are, besides some similarities which appear in this u prime minus u and u minus u prime terms that appear in the beginning of the approximation for the 5th Poisson bracket, in the set of the 9 Poisson brackets that we compute, there are many other terms which emerge from the computations with the Poisson bracket, and it's too involved to obviously describe what's going on in this type of presentation in this setting for it, but it's described in the paper and how each one of these individual terms emerge from highly non-trivial computations with the Poisson bracket. And by and large, a lot of the very non-trivial parts of these computations in the 2 dimensions for the 2-dimensional transfer matrix emerge from the Poisson bracket, because we have to look at different ways in which several factors from either the Pauli bases or other terms which appear in the parametrization from the L operator that we inject into this quantum inverse scattering formalism, how we accumulate quickly several terms which make some of the computations for the approximations of the Poisson bracket pretty complicated. And like we have been just saying, there are many complications that are involved in these arguments for determining aspects of the Poisson structure for the 2-dimensional inhomogeneous 6-vertex model. And for the 3-dimensional 6-vertex model, we should still be able to expect to compute several Poisson brackets. And but the good news is that once we have an idea about how many of the Poisson brackets are involved in one set of relations from the Poisson bracket of the entries of a higher dimensional transfer matrix, we're able to, in a sense, have some idea about everything, about all the remaining relations on all the remaining terms and the remaining computations with the Poisson bracket. Because like we said in this slide that we're going to reiterate from the previous presentation, is that we have many terms that we pick up from products of entries of Pauli operators, and these Pauli operators come from the terms that are introduced for the basis in the parameterization of the L operator. Besides that, we also have another Pauli Z basis operator, which comes into play, which is dependent upon a sign term. And this presents many non-trivial expressions which are used to help us get a handle on how to approximate, in some type of asymptotic sense, the Poisson brackets for the entries of the monodromy matrix, and how this inherently relates to properties of the Hamiltonian flow and the integrability of the Hamiltonian flow, and how this can be adopted for higher dimensions. And like we were saying, in summary from the previous presentation, to close out our discussion for the recap, we further describe computations with the Poisson bracket on different pairs of the entries of the transfer matrix in 2 dimensions. So like we had said in the first line, we saw some similarities between the approximation for the first Poisson bracket that we get from the approximation from the second Poisson bracket. But then when we reach to the 5th Poisson bracket out of the 9 Poisson brackets in the relation, there are a lot of non-trivial terms which appear, which make the computations with the Poisson bracket really complicated. And we'll reiterate some type and recap some types of properties of the Poisson bracket at the end of the presentation and closer to the end, and how we can basically make use of, the anti-commutativity, the bilinearity, and the Leibniz's rule from those 3 out of the 4 properties of the Poisson bracket, and how that comes into play for demonstrating that an integrability condition holds for the inhomogeneous Hamiltonian flow. And so very similar sets of relations for the Poisson bracket that are obtained, which relate up to permutations of entries of the inhomogeneous transformations to computations of the Poisson bracket for the 9 terms appearing in the first set of relations. And so we already reiterated this in the previous presentation, but we have a B1 prime term, and we can permute this term with the C1 prime term when we're looking at neighboring sets of relations from the Poisson bracket, and how having an idea, like we had just said a couple of slides ago, about one set of the Poisson brackets can help us understand characteristics and properties about the computations with the Poisson bracket for all the other remaining relations, and how we should expect this to hold for the 3-dimensional transfer matrix, the 3-dimensional quantum monodomain matrix, and other related 3-dimensional objects from the universal R matrix construction. And so like we had closed out in this last presentation, was that our concluding remarks is that we provided further information on computations with the Poisson bracket for QISM type methods in 2 dimensions. And we've been drawing a lot of connections and parallels and trying to answer different types of questions in these types of presentations in this series for 3 dimensions and giving hints. But in 2 dimensions, these computations were relying upon the fact that we have a system of relations from the Poisson bracket that are parameterized in entries of the transfer matrix. And we had approximations to a few of the first of the 9 Poisson brackets from the relation that we explicitly discussed. And we looked at the first Poisson bracket to establish many types of similarities between the entries which appear in the first Poisson bracket, the second Poisson bracket, and any of the other 9 remaining or 6 remaining or 7 remaining terms in the Poisson bracket from the relation, in which we also concluded with several similarities between applying the QISM type approach in 3 dimensions. But for 3 dimensions, we have to keep in mind that we can now carry over some notions where appropriate for studying 3-dimensional isovertex models. And we also refer to the 3-dimensional 6-vertex model as the 20-vertex model on the triangular lattice, from the fact that the 6-vertex model over the triangular lattice has some different properties from the construction of the universal R matrix, which were related to a product of 4 terms, 1K matrix, as well as 3 other R matrices, which are dependent upon exponentials, Q exponentials, or exponentials raised to the tensor product. And so the reference for adapting a higher dimensional QISM type argument, like we have mentioned, is related to this work in mathematical physics from Booz and several colleagues called Exercises with the Universal R Matrix. And so like we had mentioned, from the Poisson bracket, one looks to carry out similar computations between entries of the transfer matrix from different underlying assumptions on the R matrix, namely the fact that now the R matrix is a universal R matrix, like we had mentioned, and we had drew the attention of the viewer to the fact that there are, and like we had just reiterated, there's a K matrix as well as 3 other R matrix factors, which are given by these names, either Q exponential factors or the last K matrix, which is an exponential of a tensor product. And like we had mentioned earlier in the presentation as a recap, the task of interest is that we want to look at these different types of characteristics from algebraic properties which appear in the L operator and to determine how these algebraic properties influence the types of conclusions and types of computations that would eventually lead up to the Poisson bracket from the quantum monodromy matrix in 3 dimensions, and how, like we've been saying, there are a lot of themes and there's some feedback and crosstalk between 2 dimensions and 3 dimensions. But there's a difference because the particular L operator that we looked at applying a quantum inverse scattering type method that we looked at for the 2 dimensional case, it's expressed in terms of completely different bases relating more to quantum mechanics. And then the fact is that these bases for the 3 dimensional L operator, which we're going to demonstrate and now draw the viewer's attention to properties of the Cartan matrix, it's expressed in terms of like basis elements would have more of an algebraic interpretation or a combinatorial interpretation or even a geometric interpretation. And even though we're not going to mention those more type of geometric or algebraic interpretations, like some of those interpretations in this part of the series, in the next presentation of the series, we're going to turn a little bit of a direction to double Grothendieck polynomials and how looking at the up to Dynkin automorphism notion for the L operators, it can even be maybe, maybe it would be of interest to look at further connections between these types of areas because it's looking at more of a combinatorial algebraic geometry type interpretation from symmetric functions or double Grothendieck polynomials. And it's very much starting from a discrete probability model from the 6 vertex model that doesn't have any coloring, and how the presence of coloring can really add further algebraic characteristics to the model and other different types of objects that you would construct anyways for a quantum inverse scattering type approach. And so like we've been saying, up to Dynkin automorphism, there exists a family of L operators that can be obtained from the operator below, which implies that the 3 dimensional ice models, other systems of relations relating to integrability could be obtained. So it's just relating to the fact that if we have some automorphism, without explicitly defining what the Dynkin automorphism is, we can just think about it as a transformation or perhaps even an action on one L operator, such as the one that's given below that we've been describing has this algebraic characteristics from each one of the algebraic components from entry by entry of the L operator that we have in this 3 by 3 representation. And then we can think about how this would lead to several different types of relations from taking a Poisson bracket of the entries of transfer matrices in 3 dimensions. And so objects of interest for high-dimensional QISM type approaches in words include the fact that we have an L operator, which we have already described one such L operator as long with its algebraic characteristics that are not present in the 2 dimensional L operator, as well as we'll describe how the gauge transformation can allow us to obtain another L operator from an L operator that we already know, as well as from the fact that we can provide additional intuition for how the arguments would go for a quantum inverse scattering type approach in 3 dimensions. So this is demonstrating in words in a more general perspective and in a more general point of view how this would be related to what we're seeing in 2 dimensions, but also how maybe it could lead to some types of connections with other types of objects that I had alluded to a few slides ago, which are going to come up in later presentations in the series, and whether there's some type of unification or grand theme between these different types of objects, or what information could we get from studying these objects together at once. Because, it doesn't really matter if we're describing more of a discrete probability model at the beginning, because we can add on, like we've been saying, either from coloring, stochasticity, or other types of characteristics of the vertex model, and how this would impact any type of combinatorial algebraic or algebra geometry, algebraic geometric types of interpretations from the representation theory of the universal R matrix. And so one object of interest is that we can look at the Cartan matrix for constructing the 2-dimensional L operator. And this 2-dimensional L operator is a little bit different from the other 2-dimensional L operator that we have mentioned several times throughout the series, because it's not going to be expressed in terms of the Pauli basis, but it's helpful because it can give us an idea about how this construction for the universal R matrix in comparison to the construction for just an R matrix itself would be different, and what would be some of the different characteristics. This is saying that the Cartan matrix is a 2 by 2 matrix, which, in the reference for the exercises with the universal R matrix that we've been describing, there are a lot of different characteristics in terms of a root system and a lot of auxiliary quantities that I'm not going to mention because we don't, it's a little bit too much for this type of presentation on top of what we've already been doing. But it just gives an idea about different types of characteristics and what is the initial object that you start with from the Cartan matrix to make a different type of two-dimensional L operator rather than the L operator that's expressed in terms of the Pauli basis. But we can also look at the three-dimensional Cartan matrix from the two-dimensional Cartan matrix, which is another object of interest. And this is given by the fact that we can define another matrix, but in comparison to the two-dimensional Cartan matrix, the three-dimensional Cartan matrix, it just has a little bit of different entries, and it doesn't have as many twos or minus twos in its entries. And so from the Cartan matrices, we can introduce L operators like we have been saying for comparing different parts of the structure in 2 and 3 dimensions. So if we look at a lower dimensional analog of the three-dimensional L operator, the two-dimensional L operator, it's more simple in this case when we look at the construction of the universal R matrix from the lower dimensional 2 by 2 Cartan matrix, because we just have the Q of D factor and we have some other terms which are still related to Xi, which like we're saying, it's the function defined over the complex units, which is a mapping into a unital associative algebra, but also we don't have any D1 and D2 terms, which are appearing as tensor, like how we had said, tensor products and differential operators. So it's very much demonstrating how if we look at the lower dimensional case, we're not looking at the tensor product of two spaces anymore. And the fact that we're not looking at this tensor product of two spaces, it implies that we don't have to take a tensor product of the differential operator either to the left or to the right, like how I had defined the D12 and D2 operators, which Booz and co-authors in company discuss in their paper on the exercises with the universal R matrix. So it's already showing how we have a lot of similar characteristics, and even up to the exponential factor, it's a very similar exponential factor, just a different lambda parameter, which appears in front of the two-dimensional L operator, and how this is still related to some characteristics of the three-dimensional operator, given the simplification in the powers that we're raising these Q quantities to. And so up to a gauge transformation, we can act on one L operator to obtain another L operator, which is saying if we look on the right-hand side of this quality, we have an L hat of 1, 0, and we can obtain a L hat of S1, which is given by a different complex value parameter, which is instead of Xi12 in comparison to Xi of S12, by performing a type of linear algebra computation in which we perform, a multiplication from the left with G and a multiplication to the right with G inverse, and we're taking a gamma, a C1 factor. So I'm not defining all these objects precisely, but just to draw the attention of the viewer to the fact that it's pretty much like a conjugation type formula, which appears in linear algebra, which has the interpretation in this gauge transformation more theoretic sense that we can obtain different types of L operators rather than just making use of the Dynkin automorphism to obtain a family of L operators from one L operator that we have written down first. So besides L operators, such as the two-dimensional L operator that has entries with the types of algebraic interpretations that we've been mentioning, there also exists additional characteristics of factors for the universal R matrix, besides the factorization that we introduced for the universal R matrix in the previous presentation. So remember in how we had reiterated that the universal R matrix is composed of 4 factors. The last factor for the K matrix is an exponential of a tensor product, raising a tensor product to some exponential power, as well as the fact that the remaining 3 powers are given by Q exponentials, which have some type of combinatorial interpretation, and I haven't defined them explicitly in these presentations, but the Q exponentials are just relating to summations, of Z to the n and dividing by some combinatorial factors which appear. And so from the L operator up to Dynkin automorphism, some components of the factorization identity for the universal R matrix are dependent upon, as we can see, this type of 2 by 2 matrix. So when we have the 2 by 2 dimensional Cartan matrix and we want to construct an algebraic type of representation of the 2 by 2, the 2 by 2 matrix for the L operator, we can obtain part of related, other 2 by 2 matrices along the way, which we can put together in the factorization to obtain the desired 2 by 2 L operator. And this is one of them, which is involving a 2 by 2 matrix with Q's raised to various powers, as well as alternating signs of -1 in them. But also, other terms appearing in the factorization of the two-dimensional universal R matrix are related to similar exponentials or Q exponentials that we had introduced in previous talks in the series. But the thing is that this exponential, it's still an exponential of some H bar term, but it's involved in several other terms that we take with respect to tensor product, and we normalize this whole superposition of the tensor product by 3. So you can see for the first term, we're taking the tensor product of H of alpha with itself, or H of alpha with H of beta, or H of beta with H of alpha, in which we're permuting the order of the tensor product with, in comparison to the preceding term, to the second term in the superposition, as well as the fact that we have a final term of 2 of H of beta tensor product with H of beta. And so finally, another term appearing in the factorization of the universal R matrix takes the following form, namely, it's the Q exponential factor, in which we have some Q minus Q inverse prefactor, as well as a tensor product of some suitably defined basis elements, which I've reproduced in my preprint from the reference that the authors define in the paper with the reference for the exercises with the universal R matrix. So this is just to say that these characteristics and properties for the construction of the universal R matrix, they're still very much composed of very similar factors, whether it be an exponential, which we raise in the power of the exponential, we have a superposition of tensor products like we had here, or we can also have various Q exponential forms or terms which have different types of combinatorial interpretations from, a series of z to the n over n greater than or equal to 0, and we normalize each one of the terms in this series by an appropriate combinatorial factor. And so with the factorization of the universal R matrix understood, we turn towards comparing 2 and 3-dimensional L operators. So this is just to say that we're going to be able to highlight, in light of the 2-dimensional structure for the L operators, which we had talked about, what would be the types of interesting structures for the 3-dimensional L operators, and how that would relate to the higher dimensional case, and how that also can be used to juxtapose from characteristics and some qualities of the L operator, the 2-dimensional one that's expressed in terms of the polybasis elements that we had analyzed in the previous work to answer and describe and resolve the conjecture from Keating, Rishattigan, and Sridhar for integrability of the Hamiltonian flow for the inhomogeneous 6-vertex model, with some a priori information about integrability of the limit shape of the inhomogeneous 6-vertex model. And so, however, at the same time, keep in mind that other L operators can be obtained from the one reproduced from the reference on the previous slide, which don't have a 0 for the last entry of the column. So we can just see that directly from these two L operators, that they have a very similar exponential factor, but the sign of the power, the sign of the power of the exponential, it's opposite. But on top of that, we're dividing by 1 minus this zeta function, this complex valued zeta function, which I've been mentioning several times, is the mapping into the unital associative algebra. But there's also a difference in the 0 element here. So it's really helpful, because when we look at performing different types of computations with the L operator to obtain some type of recursive system, the fact that there's a 0 there, or a 0 even appearing anywhere else in the matrix, it can help simplify some aspects of the recursive set of relations that we want to obtain for the L operator. So, we can just look at different types of ways to, perform transformations, whether it be gauge transformations or up to Dynkin automorphism from one L operator, to be able to cut down our workload for the computations from the recursive system of the L operators, which will be then used to parameterize some type of asymptotic representation and approximation for entries of the quantum monodromy matrix. And so besides these two L operators in 3 dimensions, it can also be of interest, like we have been mentioning, to more explicitly draw out and spell out some comparisons between the L operators of the algebraic type formulation above with the 2-dimensional L operators written in terms of the polybases that we have kind of been alluding to and describing different characteristics of throughout this part of this presentation of the series. And so the L operators in the reduced monodromy matrix are related to the fact that in two dimensions, other like we had said in the poly Z basis, we need to specify a set of spectral parameters in one direction, one degree of freedom in the square lattice, as well as a collection of spectral parameters in the other degree of freedom of the square lattice. And this comes into play because we can make use of these relations between products of L operators to obtain some type of recursive set of relations, which we would also hope to be able to establish and apply in the three-dimensional case. And this is ultimately relating to the monodromy matrix, and it's also ultimately relating to all of those computations with the Poisson bracket of the of entries of the transfer matrix, which we had described and reviewed from the previous presentation in the series. And so the L operators in 2 and 3 dimensions side by side, like we have been mentioning, they exhibit some types of different characteristics. Besides the fact that the two-dimensional L operator on top has less types of, less total number of entries in the term because it's comparing a 2 by 2 to 3 by 3. It's also given by the fact, like we have been mentioning, that there are different types of characteristics from the action of the poly operator, the sign of the 2 eta term, as well as the dependency of the sign of the term with the spectral parameters of the 6-vertex model and also the poly basis. So it's saying that different interpretations and different sets of relations that we can obtain for some type of recursive approximation of the entries of the transfer matrix from taking products of the L operators, it's completely different from this type of algebraic type entities and entries or entities and entries that appear in the L operator in 3 dimensions, as well as different types of algebraic properties from these entries. And so, like we have been saying, the two-dimensional L operator continues to be helpful for analyzing the three-dimensional L operator in the ways in which the entries parameterize the quantum monodromy matrix. So for a higher three-dimensional quantum monodromy matrix, we're interested in the fact that for this three-dimensional quantum monodromy matrix, we still want to make use of some two-dimensional type of information, but rather than having some general type of idea about the types of computations we should use, the two-dimensional L operator has basis elements expressed in terms of completely different elements, which have more of an interpretation from quantum mechanics and looking at highly entangled systems like people in quantum computing or quantum algorithms do. And this is related to the fact that the three-dimensional L operator, as we're also going to further establish in the next presentation, could maybe be or could be of interest to look at from different types of algebraic characteristics of the 6-vertex model. And so, moreover, the resulting matrix from raising the two-dimensional L operator to some fixed power is greatly simplified in comparison to the resultant matrix obtained from raising the three-dimensional L operator to some fixed power, excuse me. So this is just really, I'm sure it's very clear to people, to the viewers, about how if you're looking at different products of L operators in the two-dimensional case, that's going to exhibit a vast simplification to the types of computations and recursive relations that you could hope to obtain from taking different products of L operators in higher dimensions, namely 3 dimensions. And from the three-dimensional L operator, we implement a strategy previously described earlier in the presentation from the series, which is dependent upon computing a product of 2 spectral parameters that are not held constant in comparison to a product of the L operators in which one spectral parameter is not held constant, as seen in the two-dimensional case. So it's very much saying how if you have a type of L operator, you can look for possibilities to import different aspects of the quantum inverse scattering approach from one L operator to another L operator, and how this can very much at least get us started on some type of encouraging steps towards looking at applications in some parallels, albeit in some cases contrived, between the two-dimensional case and the three-dimensional case. And additionally, with regards to the additional rows spanned by the third row in the first column of the three-dimensional L operator, we must identify the contributions of newer, higher dimensional terms in the recursive system for the entries of the L operator that are used to define the three-dimensional transfer and quantum monodromy matrices. So in a way, that how we define the transfer and quantum monodromy matrices and related some type of asymptotic approximation of the entries of the quantum monodromy matrix to several computations with the Poisson bracket, we should also expect and anticipate some type of three-dimensional version of these types of computations. And so, in words, the three-dimensional transfer matrix from the structure of the three-dimensional L operator is dependent upon mapping into the unital associative algebra, construction of the universal R matrix over a tensor product of two spaces, as well as a tensor product of differential operators. Like we had mentioned, either the D1 and the D2 terms are obtained by either taking the tensor product of D tensor product identity operator or interchanging the order of the identity operator with the tensor product in the differential operator. But secondly, the set of relations that we will have to perform with the Poisson bracket for the three-dimensional L operator consists of more terms than the 9 Poisson brackets that were originally analyzed for the inhomogeneous six-vertex model from the two-dimensional L operators. And that's like relating to several types of observations that we have mentioned, just from the fact, like we had mentioned, that we have to look at varying one spectral parameter in the two-dimensional case because we're holding one spectral parameter constant. But in a three-dimensional case, like in these 3 degrees of freedom that are orthogonal to each other, like in the triangular lattice or in higher dimensional spaces for the six-vertex model, we have to introduce additional set of spectral parameters, and we have to look at varying one spectral parameter, then holding it constant, and then varying another spectral parameter, which will be tantamount to looking at different amounts of terms in some product that we're ultimately going to take the trace of to form some type of transfer matrix. And just previously to reiterate and to close out this part of the series, like we had mentioned, is that when performing our computations, we heavily make use of the following properties of the Poisson bracket. So whether we're looking to do the computations with the Poisson bracket in 2 or 3 dimensions, we're still going to have to use these arguments and properties of the Poisson bracket. But the difference is that, when we're looking at the 3-dimensional case, we're going to have to compute the Poisson bracket of more terms rather than just the 9 terms that we had originally introduced from the structure of the polybases, which are injected in the formulation and the definition of the L operator for the 2-dimensional case. And so really we make use of probably the most anti-commutativity, bilinearity, and Leibniz's rule. And so the concluding remarks that we want to close out this presentation of the series is that we further distinguish between 2-dimensional and 3-dimensional characteristics of the six-vertex model, and we describe how the 2-dimensional objects carry over into the 3-dimensional case, which have ramifications on how the transfer and quantum monodromy matrices are constructed in 3 dimensions. And we alluded to several differences with, in many cases, a few similarities between constructions of the L operators in 2 and 3 dimensions. And, we just have to kind of take that of how it is, because there can sometimes be a lot of different types of properties of models of statistical mechanics, quantum physics, or even other areas of science or physics or math, which may not hold or transfer over to higher dimensional cases or where you vary other types of parameters in the model. So it's just really depending upon a case-by-case basis in the particular type of model that you want to consider, as well as the fact that, different types of models, they can raise different complications for the transfer matrix or the quantum monodromy matrices or any type of other types of arguments or computations that you want to pursue that are of interest to you. And so further future presentations in this series will turn towards other algebraic characteristics of the six-vertex model. And thanks for watching.